Hi, everyone. Welcome to the second part of chapter 9. Uh, I know in the first part, we talk about two concepts, okay, two major parts of this chapter. The first one is how do we classify chemical reactions, especially how do we learn a type of reaction called redox reaction, and how do we play with the oxidation numbers and study these types of redox reaction. Then secondly, we talked about the reaction basic concepts, the collision theory, to explain why a chemical reaction can take place and what needs to be satisfied for a chemical reaction to take place. And then we discussed what affects reaction rate by using the collision theory to explain these factors, and then the energy issue, an energy factor about chemical reaction that is endo or exothermic. And today we're going to study chemical reactions that are reversible, and also talk about a very important concept called chemical equilibrium. So let's take a look at this reaction on hydrogen and iodine to produce hydrogen iodide. This is a very classic example. I mean, no matter where you're learning fundamental chemistry or general chemistry, this is the example used a lot to explain reversible reaction and chemical equilibrium. So reversible reaction basically means traditionally when we study reaction is we're getting a reactants and all the way to form products, right? But reversible reaction means the products will convert back to reactants at the same time when the product is produced. So you're looking like in a back and forth, like two-way traffic. So that's the basically definition of reaction. The conversion of reactants to products and conversion of products back to the reactants are happening at the same time. You can see the arrow of reversible reaction, instead of a single direction arrow, we have a double arrow that shows reversible, right? But technically speaking, okay, even though we never mentioned that before, we use single arrow before for all the reactions or equation we have shown so far in this chapter. All reactions are actually technically reversible. Okay, all reactions are actually reversible. But sometimes because the reverse process is too slight, it's so slight that we assume the reaction has gone to completion. That means you don't detect any reactants available. That means the reverse process happening is a very tiny, slight amount, but it's still not absolutely zero. Like I said, all reactions are reversible. It's just sometimes the reverse reaction is so slight we neglect it. We assume the reaction has gone to completion. That's why we use a single arrow. But technically speaking, all reaction can be represented as a double arrow, reversible reaction. Okay, this is what it means. Now, let's take a look at some feature about a reversible reaction, or what happens when a reaction is reversible. Okay, the left side of the chart shows you the rate of forward and reverse reaction. Rate means how fast each direction goes, right? In the beginning, we only have reactions, okay, like hydrogen and iodine. So we know higher concentration, higher reaction rate. We're learning the factors affecting reaction rate. So we know at the beginning, the rate of the forward reaction is the fastest, okay, fastest. But as time goes by, as the reactant is consumed to get product, the concentration is going to decrease. So the forward reaction rate is going to decrease. Okay, this is what happens because the concentration of the reactants start to drop. Now, the meantime, and time zero, there's no product. Okay, there's zero product. So the concentration of HI is zero because in time zero since the time start. So the reverse reaction rate is also zero because now there isn't any product in the beginning. But as time goes by, once you get more and more product, then the reverse reaction is going to increase. right? Because more HI item produced, more higher concentration of HI, then the concentration is going to, the reaction rate is going to increase. So you can see forward reaction rate is going to drop, reverse reaction rate is going to increase. So at a certain time point, those two reaction rate will be the same, because one started with highest, start to decrease, and another one start with zero, start to increase. So at a certain time point, the reaction rate will become the same, forward and react. Okay, forward. And when they're the same, what happens? It means the reaction, what? Both ways they have the same traffic, and on and on. And that time point, we say the reaction has reached chemical equilibrium. Okay, we have seen this word equilibrium before in early chapters. Chapter 7, we talk about physical equilibrium, right? Chemical equilibrium basically means the forward reaction, reverse reaction happen the same rate. Okay, at that point, the reaction reaches equilibrium. Okay, that's a reaction rate. Okay, what happens to the reaction rate? Now let's take a look the chart on the right. Okay, what happened to the concentration of the reactants and product? Okay, we know in the beginning we have a lot of reactants, but since the reactions start to come on, the reactant concentration is going to decrease, we said, right? And then the product initially has zero, and then the product has to increase as the constant goes by. And when the reaction reaches equilibrium, with the reverse and forward reaction became the same, what happened is the reactant and product concentration will no longer change. Why? Because you have more products produced, and the same way you have more products going back, because the same rate at the equilibrium point. So at that equilibrium point, this line here shows equilibrium. Okay, at that point, then your back and forth traffic is the same. Then the reverse reaction rate will equal to the forward reaction rate, and the concentration of the reactants and product will no longer change. You can see that they both flat out. Okay, they're both flat out. It means what? Their concentration remain the constant now. Not the same, but constant. Means what? You don't increase product anymore. You don't decrease reactant anymore, and vice versa. Why? Because at the same time, again, you have more HI produced from the forward. You have the same amount of HI decomposed backwards, because the rate is the same. So the concentration of the reactants and product remain constant at equilibrium. This is what we need to know about equilibrium. Equilibrium means reverse and forward reaction rate means the same, but the concentration of the reactants and product, not the same, but they are constant. That means they don't change anymore. Okay, they don't change anymore. They don't have to be the same, but they don't change anymore. Why? Because reverse and backwards are the same. So these are some chemical details about a chemical equilibrium. Okay, chemical equilibrium. Now, once the reaction reaches equilibrium, we have a mathematical equation. Okay, mathematical equation to describe the location or the position, I should say, of the chemical equilibrium. That mathematical term is called equilibrium constant, KEQ. K stands for constant, EQ stands for equilibrium. So the expression of equilibrium constant is shown here. The bracket means concentration. So you can see that it is the product concentration, C and D are product, over the reactant concentration, A and B are reactants, and raised by the exponent of what? Of their respective coefficient. Okay, Y is the coefficient of C, Z is the coefficient of D, W and X are coefficient of A and B respectively. So the concentration of the products over the concentration of reactants powered by their coefficients. This expression is called equilibrium constant. Constant means what? Because the concentration don't change anymore. Remember, after each, so the constant is a constant value. It doesn't change as long as you have an equilibrium. Okay, as long as you have an equilibrium. So, for example, in this equilibrium constant reaction, this guy decomposes to these two, and this is equilibrium. So we can express K as this. You can see that the concentration of CO and H over the concentration of CH3OH3 and powered by the coefficient. That's why there is an exponent of 2 on hydrogen, because the coefficient of hydrogen is 2. The other one coefficient is 1. So again, K, this equilibrium constant, expressed as product concentration over reactant concentration powered by their coefficients. Okay, coefficients. Of course, bracket stands for concentration. Okay, and here are some facts, kind of like showing you the overview and the importance about equilibrium constant expression. Again, the square brackets refer to concentration, molar concentration, mole per liter, and molarity. Product concentration is always placed in numerator. It means the top. Reactants are on the bottom denominator. Okay, and the coefficient in the balanced equation determines the powers. Okay, the exponent to which concentration are raised. And more importantly, something we didn't mention and we will mention now is the last two facts. Okay, the last two facts. The first one is owning concentration of the gas and also the concentration of a solution are included in the expression. Okay, you have to take a look at the physical state of each reactant and product. Owning gas and solution reactants or substances or products are included in this expression, because owning gas and concentration, gas and solutions, they have a concentration. Okay, that means the last item, pure liquids and pure solids. If they're solid or liquid, it means they're pure. That means their concentration is 100%. It's 1. So you don't include them into equilibrium expression because they don't have a concentration. Their concentration is 1. Okay, keep those two in red in mind. Very important. Okay, only include gas or solution in the equilibrium constant expression, because these two types of substances, they have a concentration. Pure solid and pure liquids, they are pure, so their concentration is 100%. They never include them in the equilibrium expression. Okay, in the equilibrium expression. Next, let's take a look. What does it mean when we have an equilibrium constant K? Okay, it's just a mathematical equation, means we can calculate it. We have the concentrations. But what does the number mean for each K? Okay, for each K. Remember, K is product over reactant, of course, powered by the coefficient. So if K is a large number, okay, K is a very large number, means what? You have a huge amount of product and tiny reactant. That's why you can get a larger number, because remember, product divided by coefficient concentrations. So if K is a large number, then the equilibrium favors a lot for the product, because you have a lot of product than reactants. Okay, a lot of product than reactants. On the other hand, if K is a small number means product is tiny, reactant is big, because product divided by reactant, you can get a tiny number. If K is a small number, so product is small, tiny, that means what? The equilibrium favors to the reactant, because you don't even get any product because product is small. So the equilibrium position in this case, far to the left, okay, to the reactant, because product it is tiny. Of course, if you have a medium level K, that means you got both reactants and products. Okay, for example, if your K is 1, means what? You get equal kind of equal amount of concentration and reactant product if the coefficient is both all 1. Okay, but again, large K means reaction favors the product to the right. Small K means the reaction favors the reactant to the left. And medium-sized K, okay, medium-sized K means you got both the reactant and products in that equilibrium, right? So that's what the number means. Okay, let's Keep looking. Okay, keep looking. Now, if the equilibrium favors one side versus another, for example, favors reactant or favors product, sometimes we can use a double arrow, but by different lengths to show you, hey, which position does the equilibrium lies in? Okay, for example, in the following equilibrium, you can see that this is a double arrow, means it's equilibrium, but the arrow is much longer to the left, to the reactant. This means this equilibrium favors what? Favors to the reactant. Okay, you got only tiny to the product, because reversible reaction favors the reactant in this case. Okay, so we can use a half arrow in different lengths of the arrow to show which side does the reaction favors, or is the equilibrium located or positioned on. Okay, now here are some practice for you. Okay, 3 reactions, 3 equilibrium processes. Ask you to write their equilibrium constant. Okay, this is some practice. Again, keep in mind what we have here. Okay, what we have here, you should have no problem of writing the expressions. Okay, K equal to products over reactants powered by their coefficients. So all you need is to show that expression. But 2 things don't forget. I said some facts about equilibrium constant expression. That is, only gas and solutions have concentrations will be included in the equilibrium constant. But solid and liquid, because they're pure substance, their concentration is 1. You don't include them in equilibrium constant. For example, I pick the second one, the B. If you look at the equation, it is a decomposition reaction, but the reactant and one of the product is what? Are both solid. So that means when you write the equilibrium constant K, okay, write the equilibrium constant K, this one, write the equilibrium constant, because these 2 are both solid, you don't need to include them in the equilibrium constant expression. So only thing you have is the concentration of carbon dioxide and powered by 1, of course. So basically K equals to what? K equals to CO2 concentration. That's it, because the product over reactant, you only got the product. The other 2 are both solid, you don't even use them. So the equilibrium constant expression for this equation is simply CO2 concentration powered by 1. Of course, the coefficient is 1. Okay, again, I just want to remind you and show you again, use them as a practice, and you should have no problem writing a expression for equilibrium constant. Now, finally, for the equilibrium constant expression, we know from an equation we can write the expression by using what we have learned, product over reactants powered by the coefficients. And because of that definition, we can also do it backwards. If I have an equilibrium constant expression here, shown here, for example, I can even write the equation based on that, because we know substances on the top are what? Are the products. Substances on the bottom are what? Are the reactants. So basically that ratio line dividing separate reactants power and also product on the top. And we know the coefficients of the reaction is the exponent of each concentration. So each concentration exponent, the powers, basically tell us the what? The coefficients. For example, for reactant, the coefficient is 4 and 5. See, 4 and 5. For product, the coefficient is 4 and 6 for each. So you see that with an expression of the equilibrium constant, you can actually going back to write the chemical equation if needed. Okay, based on again how you understand what is equilibrium constant expression. Right now, our last topic of this chapter, that is still following the equilibrium, chemical equilibrium, again, forward and reverse reaction rate, which is the same. That's why there's equilibrium. Now, once the reaction reaches equilibrium, it will always be under equilibrium unless some factors or some external condition disturbs it. Okay, when an equilibrium is disturbed, okay, disturbed, remember the reaction rate are the same before, okay, equilibrium. But once it's disturbed, there only be two scenarios. One scenario is the forward reaction will speed up to give you more product. Or another one is the reverse reaction speed up to give you more reactant. So either one of those. Okay, once you disturb an equilibrium, you either increase the forward or increase the reverse because originally they're the same. So what we want to know is if we disturb an equilibrium, which direction does the equilibrium shift? So we either get more reactant or more product. And of course, eventually, after disturbance, the equilibrium will reach a new equilibrium again. Okay, depends on after it is shifting. But what we want to figure out is how does it shift? Which direction does it shift? Does it shift to produce more reactant or produce more product? And that's what we have to learn for this part. Now, in order to understand how do we determine the direction of an equilibrium shift, we introduce this very famous principle that will help us to determine. Okay, this principle is called forgive me my pronunciation as it is the Le Chatelier's principle. It is basically named after a scientist telling us when a stress, disturbance, change of condition is applied to a system that is already in equilibrium, how does the system adjust? Okay, how does the system shift to response to that disturbance? And this principle indicates that the system will readjust in a direction, okay, keeping that in my direction. What direction? Reduce the stress. Okay, reduce the stress. Okay, reduce the stress. That's the key for the principle. That's the key for us to understand how does equilibrium shifts when a disturbance is applied. Okay, in order to explain this principle, I want to show you this very simple physical experiment, not even a chemical reaction, but this experiment will show you what Le Chatelier principle means. Okay, think about this two tanks is connected, a big tank, a small tank, right? Doesn't matter the size, they're connected. So the water level will be the same. That one we can use that to mimic an equilibrium, right? It's a perfect equilibrium, it's the same. Now, imagine if you add water to the left tank, that means you're doing some disturbance, you're doing some alternations. Then what happens? Every one of us can have experience, life experience would know, oh, the water is going to what? Going to flow to the right, flow to the small tank because you add water to the big one. So see, after the water flows to the right tank, that means the equilibrium shift to the direction, to the right. And why it shifted direction to the right? Because it can reduce the stress. What is the stress? Add water to the left tank. The system want to get rid of some of the water by shifting to the right. So that So the water level will reach the same again. But the new water level is still higher than the original. Why? Because you added water. That is why the system is only reducing the stress, not taking away the stress. The stress is there. Again, adding water, originally the same, adding water, the water will flow to the right. So the new ones will have again. That. So the system is basically reducing the stress. The stress is adding water, reducing the stress. So the new water level will be same again. But the same water level, the new level will be higher than the original. Okay, even though the stress is reduced, but you still have a stress which is higher than the original. So this experiment is the one that demonstrates Le Chatelier's principle. Okay, with that, let's take a look at a few cases. Okay, few disturbance when we have a real chemical reaction. Okay, this is a very simple equilibrium. You can see N2O4 produces 2NO2. Okay, very simple equilibrium. The system will shift if you change the concentration. Okay, if you change the concentration of reaction product, in this case, the reaction product is very simple, 1 and 1, right? So if you add product, for example, on the left picture, if you add product, that means you have more product. The system will go into what? reduce the product by shifting to where? To the left. Okay, only when the system shifts to the left, you can reduce the product because product will be converted to the reactant. So if you add product, then the product is going to decompose or not decompose. The product is going to be converted to the reactant. So the equilibrium will shift to the left so that they're the same again. They're not the same. The rate is the same again, okay, basically. So adding product will cause the equilibrium to shift to the left. And same, adding reactant will system-wide to reduce the reactant by what? By shifting to the right to get more product. So see, that's called reduce the stress. Always keep that in mind, reduce the stress. Adding reactant, shift to the right. Adding product, shift to the left so that the stress is reduced. Okay, it is reduced. And vice versa if you remove something. Okay, if you remove something. Now here's another picture. Okay, very also perfectly demonstrate what reduce the stress mean and what direction does it shift to. Okay, I like this scheme and show you the reduce the stress. Okay, this is the equilibrium shown here. Hydrogen, nitrogen to produce ammonia, which is balanced. Okay, this picture left 1A shows you the original amount. You can see 575. Okay, these numbers doesn't make too much. It really doesn't make, you don't need to worry about the real number making sense or anything, but just show you originally when the equation reaches equilibrium, these are the concentration of these three guys. Okay, 575. Of course, hydrogen, nitrogen are reactants. Now, imagine I add 3 hydrogen. That means the reactant. Okay, add 3 hydrogen on top of the hydrogen. So that means you add the stress of the reactant. Then the system will try to reduce some of the hydrogen. Okay, how do we reduce hydrogen? The equilibrium has to shift to the right to get product. Okay, to reduce hydrogen, shift to the right. Okay, shift to the right. Now, after the equilibrium shift to the right, that means hydrogen amount will be what? Will be reduced. You can see that 3 times 7 is 10. After that reduce, it becomes 8.3. But it's still higher than 7. That means what? The stress is reduced, not taken care of. Okay, and also you can see that because you only added hydrogen, after the equilibrium shift to the right, some nitrogen will also be consumed too. You can see that nitrogen concentration is no longer 5, but what? But 4.4. Because you need some nitrogen with that hydrogen to get ammonia. And at the same time, ammonia concentration becomes 6.1, which is higher than 5 too, because after the equilibrium shift to the right, you get more ammonia. So nitrogen decreased, ammonia increased. Hydrogen is still increased because you added hydrogen, even though some hydrogen will be consumed to the right to move to the right. But overall, in the end, your hydrogen will still be higher than before because, again, we're reducing the stress. Okay, reducing the stress. So this picture, I want you to further digest it to see, oh, what does it mean shift to the right? How come the concentration of each one changes when the equilibrium shift to the right? Nitrogen will decrease because when it shifts to the right, will consume more nitrogen. Ammonia will increase when you shift to the right, you will get more ammonia. Okay, that's why the numbers. Okay, the change of the numbers will tell you a story, not the numbers themselves. All right? Concept check. Okay, this is the equation showing you an equilibrium, water, carbon monoxide to produce water, and hydrogen and carbon dioxide. So says this reaction reaches equilibrium. Then the disturbance is add water. Okay, add, let me erase it. Okay, add, see if we can write, add water. Okay, add water. When you add water, we know water is a what? Reactant. So we know the equilibrium will shift to the right to take away some of the water added. Okay, so how does the equilibrium shift to the right? Shift to the right. Now, how does the concentration of each chemical compare to the original? Okay, we know when the equilibrium shift to the right, some CO will be consumed because going to the right. So CO concentration will decrease. Okay, will decrease because CO is consumed. Now, meanwhile, when the equilibrium shift to the right, you're producing more product. Of course, so hydrogen will increase and CO2 will also increase because you're getting more product. And finally, water. Okay, we know water is the stress added. When you add water, even though some water will be consumed, but in the end, the water will still be higher than before because the stress is reduced. You still added water. So in the end, the water concentration is still increased. So this is how does the concentration of each one compare to the original? Water is still increased because water is added, even though some water is consumed. CO is consumed, so CO will decrease. Hydrogen and carbon dioxide will increase because they are the products. And the equilibrium shift to the right again, again, because of adding water, right? So I'll give this up to you, okay, up to you. Very similar to the previous one, but instead of adding water, this time you add more hydrogen, okay, adding product, and see if you can analyze that and tell me which direction does the equilibrium shift, and also the concentration of each, how do they change? Okay, I hope you can use that. And just like I did, analyze the previous one and analyze the same thing using this example, right? Next factor besides concentration change is change the temperature. Okay, change the temperature. When temperature is changed for an equilibrium, this story has to be told in two different cases. Because remember, temperature change, basically you're adding or removing energy. And that is depend on whether the reaction is endo or exothermic. So that's why we have to do it in two separate cases. When the reaction is endothermic, okay, guys, we talk about endothermic. And if you forgot, pause the video or going back to endothermic, that slide, what endothermic means. Endothermic means absorb heat. Okay, absorb heat. So basically, a simple way is you can actually write heat as a reactant, because endothermic reaction, you're absorbing heat, you're taking in heat. So heat is kind of like a reactant. Again, heat is not a substance, but you can assume heat as a reactant because it's absorbing it. Okay, that's how you, again, easier way to understand the temperature effect. Now, because heat is considered a reactant in endothermic reaction, you can understand the temperature change. Increased temperature means you add heat. If you add heat, now heat is a reactant, so the equilibrium shift to what? To the right. Okay, because adding reactant shift to the right. And if you decrease temperature, it means you take away heat. If you take away heat, the reaction will go back to the reverse side, shift to the left to produce more heat because you take away heat. And of course, because shift to the left or right, in this case, is not adding a substance, they're adding heat. So the amount of the product and reactant relatively will increase or decrease. The relative amount of will increase, decrease. So in this case, the K is actually changed. If you shift to the right, you get a larger K, more product. If you shift to the left, you get a smaller K, less product, okay, more reactant. So changing temperature will actually change the constant. Okay, change the constant. Previously, adding reactant product don't change constant. Okay, K will be the same at the new equilibrium. Okay, at a new equilibrium. Now, the second case, if you have an exothermic reaction, we know exothermic is what? Releasing heat. If heat is released, we can write the heat as a product. See that? Because you're giving off heat. Heat is what? Produced. So you can put heat at the product. Again, it's not a real product, but you can put heat on the product side. So take a look at temperature. If you increase temperature, you increase heat. Increase heat means increase product. So the reaction will turn, equilibrium will turn to the left, right? To get rid of some heat. Similarly, if you decrease heat, you're taking away heat. So the reaction wants more heat, reduce the stress. So gonna shift to the right to produce more heat. Okay, produce more heat. So these two charts would beautifully tell you, hey, how do we determine the temperature change affecting equilibrium? Just write the heat as a product for exothermic or reactant for endothermic. Then you can determine temperature change. because increased temperature means you're adding heat. Decreased temperature, you're removing heat. Then think about which direction as it goes, right? So that's temperature change. Okay, this picture shows you an experiment of temperature affecting reaction equilibrium. You can see that this reaction, apparently heat is written as a product, so we know is exothermic reaction. If you put the reaction in ice, means decrease temperature, remove heat. Okay, remove heat, taking heat away. Let me see. Write on it. Let's see, it's challenging. Let's see. When you put in ice, means remove heat. Okay, remove heat means what? Your system want to produce more heat. If you want to produce more heat, you have to go forward, because forward reaction releases heat because it's exothermic reaction. So if you put ice, decrease temperature, you're removing heat, then the equilibrium will shift to the right to produce more heat. And shift to the right, what happens is what? More pink cobalt water hydrate will be produced. So you can see the solution turns to more pink. Okay, to more pink. Of course, if you take it out, put in hot water, then the reaction will turn to the left. You will see more blue. Okay, that's an experiment demonstrating the effect of temperature change on equilibrium. Okay, the third effect is pressure. Okay, pressure. Of course, when you have a pressure as a factor, it only applies when gas is involved. Okay, because only gas affects the concentration of pressure. Okay, pressure. And also, when gas is involved, the change of pressure is actually affecting the equilibrium via volume. Okay, you're changing pressure, but in fact, it is the volume that affects the equilibrium. Okay, remember we studied Boyle's law. Okay, Boyle's law means if you increase the pressure, you're decreasing the volume. Okay, this is on the right side, on the left side, decrease the volume. So when you decrease the volume, the reaction tend to what? Move to the direction with smaller volume, because you're too crowded, right? Too crowded. So if you look at this reaction, on the left side, there are 4 molecules. On the right side, there are 2 moles of molecules. Okay, 4 and 2. So if you increase pressure, decrease in the volume, then the reaction will shift to the right to produce more ammonia, because you're using 4 moles to produce 2 moles to decrease the amount of gas, so that the volume can be what? Smaller, because it's again too crowded. The same on the right, if you decrease the pressure and increase the volume, that means you have more space. Then the system will what? Will produce more gas. Then the system will shift to the left, because left side has more gas, 4 moles of gas versus 2 moles of ammonia. So again, in pressure only applies for gas, and the gas is affected by volume change. Okay, by the volume change. Decreasing the volume, shift to the side with less gas, few moles of gas. Increase the volume, shift the equilibrium to the direction with more moles of gas. Okay, this is a quick exercise and concept check. You can see this equilibrium. Okay, this equilibrium has 3 substances, 1 product and 1 reactant, 2 products. They're asking what is the effect of adding CO2? We know CO2 is a what? Is a reactant. Okay, is a reactant. Adding CO2 will shift the equilibrium to what? To the left, because adding CO2, you're adding CO2 concentration in this reaction mixture. So shifting the equilibrium to the left. But if you're adding, okay, if you're adding calcium carbonate, okay, you're adding calcium carbonate, because calcium carbonate is a solid. We know calcium carbonate, the concentration is 100%. No matter you're adding how many calcium carbonate, concentration is still 100%. That means adding calcium carbonate, which is a solid, would not affect the equilibrium, because you're not changing the concentration of it, right? So adding CO2 will shift the equilibrium to the left, but adding calcium carbonate does not affect the equilibrium. Okay, this one, what is the effect of decreasing the volume? Okay, you can see that this reaction is very similar to the previous one. You only have one gas on the right side of the arrow at the product. So you decrease the volume. Okay, means make it more crowded. The reaction tend to go to a direction with less gas. How do we produce less gas? Move to the left, because the left is solid, right? We use gas and a solid to produce another solid. So when you decrease the volume, okay, the equilibrium will shift to the left to get rid of some of the gas, few moles of gas, because in a direction with few gas, if the volume is smaller. And increase the volume, of course, the opposite direction. Okay, and last question is adding an inert gas. Okay, this is also a note you need to make on your own, or may have a note in the bottom. Adding an inert gas does not affect equilibrium position. Okay, because the inert gas again does not change the concentration of the reactant or product. So adding inert gas does not have any effect on equilibrium. Okay, and this one is about temperature. Okay, it's about temperature. I want you to use as a practice. Okay, temperature, and also they tell you the reaction is endothermic, means it's absorbing heat. Okay, absorbing heat. So heat should be written as a reactant or product. Think about it. This is endothermic. And after you decided with heat is whether a reactant or product, you can determine the effect of temperature. Again, I leave it up to you, and heat should be provided. Here is another one telling you this reaction is exothermic. Think about it again. Do you need to put heat as a product for exothermic or reactant exothermic? And then you can determine the temperature effect. Okay, and finally, the last effect, I mean, it's not really effect of changing equilibrium is catalyst. Okay, catalyst. Remember earlier we talked about catalyst are something that participate in the reaction by reacting with the reactants or products, and then lower the activation energy, okay, to speed up both forward and reverse reaction. But because of the fact that the catalyst actually speed up both reverse and forward reaction, because the pathway is the same. Okay, you're doing the same pathway of going forward and backwards. So the effect of catalyst is speeding up both the reactant and or for the left and right side of the reaction rate, or forward and reverse reaction rate the same way. So adding a catalyst, you basically make the equilibrium reaches faster, but both forward reaction is still the same after you're adding catalyst. So in that sense, catalyst do not change the position of an equilibrium. Okay, again, the reason is both forward and reaction and reverse reaction rate are increased the same way, same extent. So originally, if they were the same, and after that, they're the same as well. It's just the new equilibrium is reached quickly, more quickly, because they're faster. Okay, but the position is not changed by catalyst. Okay, so that's the last one of the factors of changing the equilibrium position. Okay, and again, make sure you study, understand fully what Lachlan-Leer's principle, know these factors, the concentration, the temperature, and the pressure, and also finally catalyst and inert gas, and how these affect the position of equilibrium. And make sure you use these practice as an exercise for you. And that is all for chapter 9. Again, any questions, please feel free to ask me, and even confirm the key for these practices, or ask me to explain to you. Feel free to contact. That is all for chapter 9. Bye now.